So hello, welcome to everyone in this video. This is part 3 of the part measurement unit of the microwave. This is the lecture number 11. We already covered up the those portion, that is the transmission line and waveguide and component. This portion already covered, and in this measurement unit we actually cover part. In the first part we take this portion, in the second part we cover up this portion, and in the third part in this video we want to discuss about this portion, that is the dielectric parameter of amorphous solid, dielectric constant, AC conductivity, resistivity, inertion loss, return loss, shielding coefficient. In this video we want to discuss about this portion. If you wants to watch the previous lecture, you can go through this description box, the link given in this description box, right? So let's start with this portion about the dielectric material parameters of a amorphous solid. You can refer to this reference book for this portion. So at first we want to discuss about the amorphous solid. Actually, in the crystalline solid, crystallines means in the total solid, if this is a q or any solid material, if this is a any solid material, if you wants to take an cross section area, this is a cross section area of any solid material. You can see here the dipole or the orientation, or you can say the arrangement. Actually the arrangement will be uniform throughout the material. If you take the throughout the material, if you take the total material, the arrangement will be same. That's mean in the simplified format we can say the arrangement like that. In the portion there is a atom here. Okay, this is called a crystalline structure, where all over the material the structure are repeated. If you take any part of this material, you get same structure. This is called crystalline crystalline structure. This is called crystalline structure, that is all throughout the material, throughout the material, throughout the material, the throughout the material, the arrangement, the arrangement of crystalline, the arrangement of crystalline will be same, right? Will be same. If you take any portion of this material, you will get the same structure of the crystalline. This is called the crystalline structure. And in some structure, in some material, you can say in this portion there is a some arrangement. You can see there is a portion where there is another arrangement. Okay, so there is a crystalline but in a small region, like that. In this portion will be like that. Clear? So in the portion will be like that. So you can see here there is a crystalline but in a small range. This is called nanocrystalline, nanocrystalline structure, nanocrystalline structure. That is the crystalline in small range. Crystalline arrangement, crystalline arrangement in small region, in small range, in small range, right? So in small range there is a crystalline is called nanocrystalline. Sometimes in between these two, that is crystalline and nanocrystalline, there is a microcrystalline, but this is does not use generally. Microcrystalline, microcrystalline, but this is not useful. Actually crystalline, then nanocrystalline, and then another arrangement. This is not crystalline structure anywhere. This is called amorphous. This is called amorphous. There is not arrangements like that. This is a haphazard arrangement. Okay, this is a lines, crystal lines. This is called amorphous arrangement or structure. Okay, amorphous structure. Okay, there is no crystalline at all. No crystalline, no crystalline at all. This is called amorphous solid. Clear? So there is mainly three types. There is mainly three type structure in the solid structure. Will be get crystalline structure, nanocrystalline structure, and amorphous structure. Okay. In case of in compared to conductivity, you can say the conductivity of crystalline structure is very much greater than conductivity of nanocrystalline structure compared to the amorphous, right? This is will be the arrangement of the conductivity. And if you take the production cost of crystalline is greater than the production cost of nanocrystalline, then the production cost of amorphous. Okay, so the production cost of amorphous is lower compared to the crystalline. That's it. But here is important, the conductivity of amorphous is lower in case in sometimes this behaves like a dielectric material. This behaves like a dielectric material. Okay, is sometimes its conductivity much lower, such that it behaves like a dielectric material. Actually, in case of proper or actual amorphous structure, this behaves a dielectric material. Clear? So that's why we want to discuss about the dielectric constant of amorphous solid. That means amorphous solids each have a inherent property, that is the dielectric property. That means its conductivity is very low, and sometimes this conductivity tends to zero. That's why this is called dielectric material, and we want to discuss this the dielectric properties of this amorphous material, right? So let's start with the dielectric constant. From the previous lecture, we already discussed about this propagation constant G for guide, waveguide. The propagation constant of the waveguide is related with this frequency, permittivity and permeability, and the this is the cutoff wave number. Kc is the cutoff wave number, which is related to the cutoff frequency, like that. Okay, so omega c was the angular cutoff frequency, angular angular cutoff frequency, which depend actually the dimension of the waveguide. Cutoff frequency, angular cutoff frequency, and omega stars is the relative permittivity. This is actually relative uh, permittivity. No, G star is the permittivity. This was actually relative permittivity. These two are relative permittivity. This is real part and this is complex part. Relative permittivity, these two both. Relative permittivity, and this is real part and this is complex part, right? So these are related like that. And gamma g also is related with the real part and imaginary part. If you square both sides, you will get this relation. Comparing the real part and imaginary part, you will get this epsilon, that is the relative permittivity of real part of relative permittivity, relative permittivity, right? And similarly you will be get the relative permittivity, complex part of the dielectric constant or relative permittivity. Okay, so relative permittivity is called the dielectric constant, you know. And if you plot this epsilon naught and epsilon, you will be get with the frequency f is nothing but omega by 2 pi, f is nothing but omega by 2 pi. So if you plot this F versus omega S, that is the relative permittivity of the solid, is follow this like of structure. That is the real part will like that change, and the imaginary part will be like that. Okay, and this is nothing but this is a part of this total spectra. If you if you change the frequency from a long range, you can see there is a different step arises like that. This actually happen due to the polarization material. That means the polarized material, when the charge are separated, they are relative permittivity like that. When there is a dipole arranges stronger, that is effective, then these are fall down. When is ionic arrangement is effective, these are fall down again, and atomic structure will be like that. Okay, so this is the real part of the dielectric constant, and this complex part will be like that. Where this change will be happening, there is a peak arises. That means these are loss factor. Actually, this is a loss factor, and this is a dielectric factor, right? So this is called the loss factor. This is called loss factor, and this is actually dielectric factor. Okay, dielectric factor, and this is actually represent the loss factor, right? And this spectra actually we will obtain by this meter. This is very useful meter, the Haiki company. This is called impedance analyzer. By this meter we can find out this spectra very easily. If there is a long range frequency meter, then you will be get total spectra. Otherwise the small range, if you know the range of this material, for a unknown material you must take the long range, but a known material you will be get the sharp change if you take the small range variation, right? So for a unknown material, this is referred to take a long range, such that you can get a total spectra. If there is a only space charge and dipole, there this transition will be happen, or dipole ionic, this transition will be happen. So depending on this material, which transition will be happen, this will be the decided by this material, right? So if for the experimental purpose, we can for check for the total frequency range, such that we can, if there are different charge, dipole or ionic or atomic, these are the all effect will be contributed or be can be collected from this data, right? So this is an important instrument by which we can get this parameter as well. With that we also get the conductance, actually conductance, impedance, loss factor, all things, and the capacitance of this dielectric material also can be find out. Okay, how will can we find out? Just discuss about here. Consider this is a glass. This is a insulating glass, and this is a material, that is the dielectric material. This is nothing but the dielectric material. This actually silicon dope zinc oxide. This is actually silicon dope zinc oxide. Silicon doped zinc oxide. This is actually semiconductor, insulating semiconductor. That is semiconductor with very low conductivity. You can say this as a dielectric material. Dielectric material. Actually, this is real. This is not a silicon dome material. You can say the alloy, silicon alloy, zinc oxide with silicon alloy, zinc oxide with silicon alloy. Okay, alloy. So for that material, here we discuss, this is that is these two are strip, that is the aluminum are connected, and if we probe with these two aluminum, then what happen, there will produce a electric field, and this electric field can be penetrate to this material as well as through this air. Okay, so these two plates like a capacitor plate, and this electric field passing through this material as well as for air also. Okay, so if you take the dimension range, you will be like that. Okay, so this can be behaves like a CR parallel. This behaves like a capacitor and with the resistance with of this material. Okay, so the total C will be CR plus C sample, because they are parallel connection, and so the sample capacitance will be like that, total C minus CR. So actually we measure the C total from this instrument, but we need to get the sample capacitance by minus of this capacitance due to air. So capacitance due to air can be find out from using this formula, and this can be taken as this for this dimension. In case of this value dimension of this value, you get the air value will be like that. This is picofarad. This is very small, but this will be countable when the capacitance of this material also be lower, but in case the capacitance of the material is higher, then this can be neglected. Otherwise you need to subtract this value from this total capacitance to get the capacitance for this sample, right? So you remember this thing, there is a two factor, that is the capacitance for this material as well as for capacitance for this air, and these are the parallel combination. Okay, so first we can get the capacitance from this capacitance can be related with this frequency. This can be find out from the Nash-Place plot, and this capacitance is related to this relative permittivity is like that. From here you can get the relative permittivity with this capacitance relation. That means this capacitance gives you the from this capacitance give you the value of the relative permittivity, real part of this relative permittivity, right? And from this relative permittivity you also got the imaginary part, and you can see this G conductance, B susceptance, Y admittance, and so on. These are related to each other, and from this figure you can see the imaginary part will be related to this real part. Clear? So this is the real relative permittivity, and this is the imaginary relative permittivity. They is related to the loss factor tan phi from this phase diagram. Clear? So this structure gives you the capacitance. First the meter, this meter actually measure the capacitance first, and after measuring the capacitance got the real part of this dielectric constant using this capacitance, parallel plate capacitance, and from this real part of dielectric constant you will be get the imaginary part of dielectric constant. So this calculation or the mathematics calculation will be happen within this material, and you finally got the value of epsilon prime and epsilon double prime, that is the real dielectric constant and the imaginary dielectric constant with the variation of the frequency. Clear? So from for the total dielectric constant is nothing but this root over real part square and the imaginary part square. Okay, so this is the mathematics what happening in this instrument, and finally we got this spectra, and from this spectra we will be get the dielectric constant, and you can idea about the material is behaves in which transition they actually behaves. You can get an idea of this material from this spectrum. And this instrument does not measure only these two parameters, this actually measure the other thing, and from this parameter we actually calculated the AC conductivity of this material, the conductivity, and this is AC because these are the frequency dependent, that's why this is the AC conductivity. And this AC conductivity actually related to this, and this conductivity relation actually formulated elsewhere. We taken this relation here only. Sometimes this is called the tangent factor, loss factor, lambda t, the conductivity. For the conductance you can get the conductivity. So the AC conductivity is nothing but total conductivity minus DC conductivity, and this actually depend in case of the semiconductor is like that: a omega to the power s, omega is the angular frequency, a is the constant, and s is the frequency exponent depend on the material. Actually we got the AC conductivity from this Nyquist plot, and by taking the value of s, actually we matches this curve. From this instrument we got the value, the AC conductivity. From this instrument we got the value of AC conductivity, just taking the Nyquist plot. And after after that, this frequency exponent will be depends after plotting this Nyquist plot, we can find out this exponent, right? This frequency exponent can be find out from this Nyquist plot. We just count this plot, and these are the parameter which can measure from this instrument. So that is the impedance, admittance, resistance, reactance, conductance, susceptance, parallel capacitance, quality factor, and phase angle, right? So this all things can be find out using this instrument. Okay, and now comes into this plot. This is actually the real part and imaginary part of impedance. There is a minus sign. Look at this minus sign. This is the real part impedance, and this is the imaginary part of impedance, which can be find out from this instrument. They actually gives the value of real part impedance and imaginary part impedance with variation of the frequency, right? So from that you can find out easily find out the value of the impedance, real impedance and the imaginary impedance, and this behaves like a this equation. This is a circle, semicircle equation. If you take the relation, actually real part of impedance and imaginary part of impedance, you can get the equation for this is like the semicircle. Okay, so this is called the Nyquist plot. For this is simply one semicircle, the equivalent circle will be like that. There is a L, R, and C R is the in the parallel combination. Okay, so this is the effective. These two are negligible, but this portion actually happening this to due to this resistance, right? And this is happening for that. When these are starting from zero, so there is also a CR parallel, right? CR parallel in this region. Since this is a gap, so there is a resistance and inductance. Actually these gaps rises due to resistance, and this gap rises because of this negative jet is rises due to this inductance. Okay, here you can see starting from 0, that's why this is CR and this is CR. Now if you take, there is a gap, again that's mean there is a resistance. This gap rises this resistance, and this portion which is CR, and this is not touch here. Then you can see there is a window layer. Actually there is a another thing. This is actually some additional effect arises. uh, capacitance effect actually gives rise in this effect. Okay, actually this is inductive effect, I think. I think this is inductive effect. And finally you got this type of expression, this type of plot. And this plot is comes when this equivalent circuit will be happen. So from this Nyquist plot you can get the equivalent circuit, and after the getting the equivalent circuit you will be get the value of the dielectric constant, AC conductivity, and resistivity also, right? And you can see from the board plot you can also get this relation. This is actually for real impedance and the imaginary impedance, and this impedance curve with the frequency, if you remember, this was the frequency impedance curve, and this is the phase angle curve will be like that. This is called board plot and this is called Nyquist plot. This can be interchanges from one to another. Okay, so here you can see this omega is infinity here, omega is 0 here. That means in this region, this is low frequency region, that is this portion is plotted here, and this high frequency region is plotted here, right? So omega is changes from that region to that direction. Omega is increases, omega is increases actually, omega is increases actually that direction, omega increase, right? So this is Nyquist plot, and this is the called the Bode plot. Here you can see this is for the first things. Here this electrostatic resistance, this portion, electrolytic resistance, difference layer resistance, increasing frequency, equivalent differential capacitance, like that. So that is, this is the significance of the Nyquist force actually written here. You can just know about this Nyquist plot. That means from this plot you can explain the nature of this material, right? uh, and you can see there is a frequency variation with this conductance. This is actually I obtained this curve in my research experience in my lab. You can see here the actual curve we actually obtained this instrument for this material, that is the silicon doped zinc oxide material. With the variation of this frequency, the conductance will be increased like that. Actually we does not get this type of expression, but because of this range of the frequency of this instrument that was I used is very low, but you can get an idea there will be a transition happening in this expression for this all parameter. And this all parameter can be find out just taking this switching or the set the value of this instrument, right? So these are the all things about the impedance analysis meter, and from where we can get the impedance AC conductivity actually of the dielectric material can be find out. Okay, now comes into the next part, that is the insertion law and return law. Insertion laws and return laws. That name suggests, insertion loss means the power returned when a signal passes through a device. When the signal passes through a device, what power will be passes, that is the insertion loss. That means inserted, so the power lost due to this insertion. This is the input power, and this is the transmitted power. If we take the minus, that is input power minus transmitted power, this is the loss of insertion. When the power is inserted within this device, there is a loss, that is called input power minus transmitted power. And the return loss, power lost upon the reflection. When they reflected, then how much power is be lost due to transmission, right? So this is the return loss, that is the input power minus reflected power. In the dB decibel unit, you can find out this power, that is minus 10 P transmitted by P input, like that. Or you can in terms of transmission coefficient, there will be 2, because the power is the whole square of this transmission coefficient voltage, that's why there is 2, so that is 20. Clear? In the case of reflected also, there is reflected power by input power. Pi is the, actually I need to write down these things, that is the P Pt is the transmitted power, or you can write here Pt RT PR and Pi. Clear? Pi incident. So that's it. So this is the transmitted power by incident power, and this is the reflected power by incident power. This gives you return loss, and this gives you insertion loss. Okay, so if you wants to how we can find out this uh, insertion loss and return loss, think about the first thing, this isolator. This actually minimizes the reflection for the signal to flow towards the generator. This portion actually minimize the reflection. This portion calibrate for this detector, and these two directional coupler, I think you know about the directional coupler, we already discussed in component. To monitor reflected and transmitted power, the monitor reflected and transmitted power, these two directional coupler. And finally this display the reflected and transmitted loss. So by this arrangement we can find out this reflected loss and the transmitted loss, that's mean inertial loss and return loss. Clear? Actually this description actually written for this figure. And you can say this dimension, that is the minimized loss and maximize return loss, is the, that means with the help of the dimension of the waveguide we can change this loss, which loss we actually want. This will be the depend on this shape. You can see this shape, actually this is twist, this is bending. Clear? This is microstrip. These are different structure which can be used to change the loss. That's mean which loss we actually need, inertial loss or the return loss. Clear? And next, the next point is the shielding coefficient. You know the shielding factor within the plasma. That's been at a certain region, if you want to confined, that is the or the plasma confined, this was actually shielding. That's mean the plasma will be shielded out within this within a region, shielding effect. That's mean the microwave also can be shielded within a region, and this can be actually find out from this transmission coefficient. So this is the shielding coefficient, or called shielding effectiveness. This is called shielding effectiveness. This can be find out from the transmission coefficient. That means how the microwave are transmitted throughout the position, throughout this material, or where the shield is are happening, shielding are happening. That can be evaluated from this formula. Clear? That's it for today, and this is your homework. You can do this by this relation, which already obtained these two relation, finding to this relation. That's mean from the value of epsilon, real part, and this imaginary part, from this alpha and beta, that is the you remember the alpha and beta are nothing but the gamma g equals to alpha plus j beta g. Clear? So you can find out actually gamma g value from these two value. Clear? So you do this yourself. I can you can do this very easily. So that's it for today. We will be meet in the next video with the help, with the take of the microstrip structure measurement or microstrip actually. Okay, this is all about me. This is my contact details, and this is my YouTube channel details. So that's it for today. Take care. We'll meet in the next video as soon as possible. Thank you.